Hello, this is Richard Hammack's Calculus 1 course. We are in part 5 of the course on integration. Today in lecture 42, we're going to make a very fundamental definition. The definition of the so-called definite integral. We've seen indefinite integrals before, and they're antiderivatives, but the definite integral is something different. The definite integral is as important as the derivative in calculus. And like the derivative, it's going to be defined in terms of a limit that gives it its meaning. But also like the derivative, where we eventually came up with rules that allowed us to bypass that limit, with the definite integral, we're eventually going to come up with what's called the fundamental theorem of calculus that allows us to bypass the limit in its definition. So with that, let's get to work on the definition of this new concept called a definite integral. Riemann sums will play a primary role in the definition of a definite integral. So before giving the definition, I want to review Riemann sums. I'm first going to talk about what we mentioned in the last lecture, Riemann sums with what are called regular partitions, and that just means you're dividing up your rectangles into rectangles with equal bases. And it worked like this. We had a function, y equals f of x, above the x-axis, and we thought about the area A contained under the graph of that function above the x-axis and between x equals A and x equals B. And we approached the area this way. We first divided the interval from A to B into n equally sized subintervals, where n is just some number, like maybe 10 subintervals or 100, n equals 10, or n equals 100 or bigger. That's just how many little intervals you have, n. And because you have n of them, you're dividing the interval from A to B into n equal pieces, and the distance from A to B is B minus A, so the width of any one of these little subintervals would be B minus A divided by n. And we're going to call that delta x. That's just the width of any one of these subintervals that you choose. And the next thing we did, if you'll recall, is we labeled these tick marks. x0 for A, then x1, x2, x3, x4, and so on, all the way up to x sub n, which was B. And we called these grid points, and the formula for each one was that x sub k would be A times k times delta x. So for example, x sub 3 is our A plus 1, 2, 3 times delta x, etc. And then we took what we called sample points inside of each of our intervals. In the first little interval, we took x1 star and called that our first sample point, and then x2 star and x3 star, and so on. And these could be anywhere in this interval between the left-hand endpoint and the right-hand endpoint. Just a little sample point in there. It doesn't really matter where it is. Sometimes you might want to be, just for sake of definiteness, take x sub k star, your sample point, to be way over here as far to the right as it could be. Or some people like to think about it right in the middle like this. Or you can have it way over on the left. Just anywhere in that little interval. But anyway, you have a bunch of sample points, n of them, one for each little subinterval. So our sample points are x sub k star. And the next thing we did is we started to form rectangles on each subinterval. And for every rectangle, its height is got by taking f of the sample point. And that gives the height of the rectangle. And its base, of course, is delta x. And so you just take f of every sample point and you form a rectangle that way. So the area of these rectangles, it's easy to compute because the area of every rectangle is height times base. So if you look at just a generic rectangle like rectangle number k, its height is f of x sub k star, f of the sample point, times its base is delta x. So the area of any rectangle, or in particular rectangle number k, is height times base, which is f of x sub k star times delta x. And at this point, we defined what we called a Riemann sum. And it was the sum from k equals 1 to n of f of x sub k star times delta x. Think of it as just the sum of the areas of all of these rectangles. Or in general, I should say, maybe not area, but height times base of each of the rectangles. Because after all, if this function ever dipped down below the x-axis, f of a sample point could be negative, and that would be, you wouldn't want to think about that as area. But however you look at it, the Riemann sum is the sum of height times base of all the rectangles added up together. Now, if the function is always positive on the interval from a to b, all these rectangles will have positive height. And it makes sense to think about this Riemann sum as being a pretty good approximation to the area contained under the curve between a and b. And the more rectangles you make this, the better and better that approximation gets, as we talked about last time. And in fact, you could say that the area under the curve, the area A, is the limit as the number n of rectangles goes to infinity of the sum from k equals 1 to n of f of x sub k star times delta x. In other words, area is this limit of Riemann sums. So we'll see when we get to the definition of a definite integral, this expression right here is going to be a part of it. But we haven't said everything about Riemann sums. Before we get to our big definition, I want to say a little bit more about Riemann sums. If you've read the textbook, you've noticed or read about the fact that you don't necessarily have to have what's called a regular partition when you're doing a Riemann sum. You could set this up so the widths of the rectangles are differently spaced. And let me talk about that a little bit. So the same picture, but we're going to make our tick marks a little bit different in this setup. We're talking now about general Riemann sums. And what you're going to do is just take a bunch of numbers between a and b, x1, x2, x3, all the way up to xn. And as you've seen here, they're in order, numeric order, they're increasing, but they don't have to be the same distance apart. So those are our grid points. A is less than x1, which is less than x2, which is less than x3, and so on, which is less than xn, which equals b. So they're in that order, but we're saying nothing about the spacing. And then you could take sample points, just as we did before, just, points that you pick of your own choosing in each of the n intervals that you get this way. Like x1, it's in the first little interval somewhere in there, or x1 star, your first sample point is in that first interval. Move on to the second interval, somewhere in there it's got to contain the second sample point, x sub 2 star, and there it is right there, kind of, to the left of center. X sub 3 is your third sample point, right in the middle of the third interval, and so on. X sub k star will be in the middle, or somewhere in your kth interval. So those we call sample points. And then the next thing we're going to do is we're going to make rectangles, just as we did before, by taking f of the sample points for the heights. But the bases of the rectangles, they're equal to the respective intervals. They have different sizes. Here's a really skinny one right there. So we make n rectangles this way, And these rectangles, they have different bases. So to recognize that and to have a notation for it, the width of the first rectangle, we're just going to call that delta x sub 1. The width of the second rectangle, that's delta x sub 2. The width of the third rectangle would be delta x sub 3. So that would be your x sub 3 minus x sub 2, etc. The width of your, in general, the width of your kth rectangle is denoted x, delta x sub k. So the delta x sub k's are the bases of your rectangles. And as before, it's easy to compute the rectangle, the area of any rectangle. The area of rectangle number k would be its height times its base. And rectangle k has a height of f of x sub k star and a base of delta x sub k. So f of x k star times delta x sub k is the area of that rectangle. Now, we're going to define a Riemann sum in this situation in just a moment. And then we're going to think about letting the number of rectangles go to infinity. But you got to be a little bit careful in the setup for this. There's one more little detail here. If you're going to let the number of rectangles go to infinity, so you have more and more and more rectangles, you got to make sure that you don't have any rectangles that stay fat, like this one. You could imagine adding in more and more rectangles out here, and they're getting skinnier and skinnier and skinnier, but this one stays the same width, and that's not good because that's not approximating the curve. So we're going to be concerned here with a number delta, which is going to stand for the width of the thickest rectangle, the largest base of a rectangle that you have in this setup. So the largest base is going to be delta. So in this picture, it looks like it's delta is equal to delta x sub 2. Okay, now we're ready to state what the Riemann sum is in this situation. The Riemann sum, like before, is just the sum of base times height of all of your rectangles. And the base of your kth rectangle is delta x sub k, and your height is f of x sub k star. So the Riemann sum is the sum from k equals 1 to n of f of x sub k star times delta x sub k. If this curve for f of x is above the x-axis, so all those heights are positive, the Riemann sum is just adding up the areas of all of these rectangles one after the other, adding them all up and getting a number. So the area, as we had before, would be the limit as the number of rectangles goes to infinity of that Riemann sum. But here you have to be careful because we said earlier that you don't just want to say the number of rectangles goes to infinity because that leaves open the possibility that some of them remain thick, like this one, and you squeeze in more and more skinny rectangles elsewhere. You want to rule out that. So what you're going to demand here in this limit is that delta approaches 0. And if you think about it, if the width of your thickest rectangle is getting smaller and smaller and smaller, you've got to have more and more and more rectangles in there to fill up that interval. So that forces the number of rectangles to go to infinity. So we would say that area A is the limit as delta approaches 0 of the sum from k equals 1 to n f of x sub k star times delta x. Just the limit of this Riemann sum as delta goes to 0. Now, I have to be quick to add here that this limit, if you really try to play around with this, you might realize that there's some technical difficulties because normally when we have a limit, like, limit as delta goes to 0, what happens or what occurs over to the right of it is some function of delta. And this expression here doesn't really depend so much on delta. It really depends on f and x, how you chose the sample points and the thickness of your rectangles, which may have widths that are different from delta.
So really what's happening in this limit is it's something that you will, if you really want to understand the nuts and bolts of it, it's something that you would talk about in advanced calculus. But the basic idea, I think, is pretty intuitive. And this is the way the textbook says it. It sort of makes sense that as the thickness of the smallest rectangle goes to 0, you get more and more and more rectangles. And so this Riemann sum, no matter how you choose the sample points, should be getting closer and closer and closer to the area A. So I would say take the intuitive approach and look at this limit that way. Okay, now with this quick review of Riemann sums, we can now get to our main definition, the definition of the definite integral. And here, let's say that x sub k star, delta x sub k, and delta, they are as defined on the previous two slides. So we're using the setup from the beginning of this lecture. And here's the definition. Given a function f of x defined on a closed interval from a to b, the definite integral of f of x over ab is the following number, okay? And that number is going to be the limit as n goes to infinity, sum from k equals 1 to n, f of x sub k star times delta x. In other words, it's that limit that gave us area in the first definition of a Riemann sum with regular partitions. And also, since the second limit for the general Riemann sum also gave us area, that number is also equal to this limit. The limit is delta goes to 0. Sum from k equals 1 to n, f of x of k star times delta x. So those are numbers. And there's a special notation for these numbers. Rather than write out this limit of a Riemann sum, we write this piece of notation to stand for that number. And you read this as the definite integral from a to b, f of x dx. So, rereading this sentence, given a function f of x defined on the closed interval ab, the definite integral of f of x over the interval ab is the number definite integral from a to b, f of x dx. And it equals this, or this. Now, all of this is provided the limit exists. If not, we say the definite integral does not exist. So that's it. We'll look at some examples in a moment. But before we move on, I should mention that you should read this as the definite integral from a to b, f of x dx. But for economy of words, sometimes we're just going to say the integral from a to b, f of x dx. And that's considered okay. Now there's a theorem in the text that says this: if f of x is continuous on that closed interval, then the definite integral from a to b, f of x dx exists. In other words, these limits exist and will equal a number. This is another one of those functions or theorems that I promised you we would see that says, or has the form, if a function is continuous, then some important property holds. And this says that if f of x is continuous on the interval, it has no breaks on the interval, then the definite integral exists. Now, we're not going to prove this. To prove this theorem, you would be in a class on advanced calculus. That's a 400 level calculus class. So accept this theorem on faith. And actually, you can prove a slightly stronger statement. It turns out that if it's okay for f to have a finite number of discontinuities on the interval from a to b, and then this limit will exist. But anyway, this theorem basically tells us that you don't have to worry about your limits your definite integrals not existing. If everything is continuous, which is the way we want to look at things anyway, the definite integrals are going to exist. I want to remark here that the definite integral from a to b f of x dx is a number, okay? It's a number. For example, think about the definite integral from 0 to 2 of x squared dx. Well, according to our definition, that would give the area under the graph of y equals f of x equals x squared between 0 and 2. And remember how we computed that in the last lecture? And it was equal to 8/3. We actually worked out the limit, and we got the limit of Riemann sums, and we got 8/3. So the definite integral is a number. The definite integral from 0 to 2, x squared dx equals 8/3. But don't confuse that with the indefinite integral, which looks like this without the a and the b. The indefinite integral of f of x dx, that's a bunch of functions, not numbers, but functions. For example, the indefinite integral of x squared dx is a set of all antiderivatives of x squared, so it's the functions 1/3 x cubed plus c, all of the functions whose derivative is x squared. So again, this new thing we're defining, this definite integral, is a number. But what we talked about in section 4.9, the indefinite integrals, they are functions. Now, you might wonder why the notation is so similar. Well, we'll see why when we get to the fundamental theorem of calculus in the next section. There's a very, very, very close relationship between definite integrals and indefinite integrals. A close relation to numbers that look like this and functions that look like that. We'll get there in time. But for now, I want to continue looking at this definition of this new idea called a definite integral from a to b of f of x dx. We're going to look at some of its properties. One of the first and most basic properties is that the integral from a to b f of x dx is equal to the area above the x-axis and under the curve, which I'm going to call a up, minus the area below the x-axis. And this requires a little bit of explanation here. Here's the graph of an f of x, and part of it is above the x-axis, and the other part is below the x-axis. And the area that's above the x-axis, I'm going to call that a up, some number of square units of area. And the area below the x-axis, we're going to call that a down. And if you think about the way the definite integral from a to b f of x dx was defined, it was the Riemann sum of a bunch of rectangles. And the ones where the function is above the x-axis, height times base is positive there. But where the function falls below the x-axis, those rectangles would have negative height. You take f of the sample point, you get a negative number. So when you work out the Riemann sum, you have a positive contribution for the rectangles above the x-axis and a negative contribution for the rectangles below the x-axis. And in the limit of Riemann sums, where you have the definite integral, that just translates to a up minus a down. So, for instance, think about, as an example, the integral from -1 to 2 of the function x minus 1 dx. And I'm going to draw a picture of that. Up from here, from the previous line, we know that's a up minus a down. And we're actually going to compute this integral by looking at its graph. Let's graph this function x minus 1. There it is, y equals x minus 1. That's just a straight line with slope 1 and y-intercept -1. It looks like this. It has an x-intercept of +1. And notice that you get some a up, which is this little triangle right there, and then some a down, which is this bigger triangle right there. So we could compute a up and also a down as 1/2 base times height for these two triangles. So the a up part, we're talking about this triangle above, that's up above the x-axis. its base is 1, its height is 1, so its area is 1/2 1 times 1. That's A up. Then you have minus the A down. Well, A down is this bigger triangle. Its base is equal to 2, and its height is equal to 2 as well. So its area would be 1/2 base times height. That's 1/2 2 times 2. And you subtract that because it's A down. And when you combine this, you get negative 2/3. So the definite integral from -1 to 2 of x minus 1 dx equals negative 3/2. Here's another example. Think about the definite integral from -3 to 3 of the square root of 9 minus x squared dx. What would that be? Well, you may recognize the form of this function as giving a very familiar geometric object. That's a circle, right? In fact, it's a circle of radius 3 centered at the origin. If you graph y equals the square root of 3 squared minus x squared, which is what we have here, that just gives you the top part of a circle of radius 3. And if you're wondering where that comes from, if you square both sides of this, you get y squared equals 3 squared minus x squared. That's x squared plus y squared equals 3 squared. That's the equation of a circle of radius 3. But since we only have the positive square root here, we just get the top part of it. Well, that's all A up. There's no A down. So this definite integral would just be A up minus 0 for A down. And the A up, we can compute that because we know a formula for the area of a circle. The area of a circle of radius 3, which is what we have here, would be, it's pi r squared, so that's pi 3 squared. But you only have half of the circle, so you have to multiply that by 1/2. So 1/2 pi times 3 squared, which is 9/2 pi. So this definite integral equals 9/2 pi. Now these two examples are a little bit artificial because we relied on the fact that once we graphed the function, it looked like a familiar geometric object, and we could use an area formula for either for triangles or for circles. You won't always be able to do that in general. But we'll quickly have ways to compute definite integrals without using area formulas from geometry. We'll use antiderivatives. But that's looking a little bit ahead. I want to talk about some other properties of definite integrals. Here's one property, and notice here it's the integral from a to a, not a to b, but the integral from a to a of f of x dx, that definite integral. Well, think about that as a Riemann sum or perhaps area where the region lies between x equals a and x equals a. So that's no area at all. So it makes sense that you would have 0 for the value of this definite integral. Another property that this looks kind of strange at first, but actually makes sense. The integral from a to b f of x dx is negative the integral from b to a of f of x dx. In other words, if you switch these a's and b's, which are called limits of integration, interchange them, that's going to flip the sign of the integral. And why would that work? Well, remember how you define delta x in the definition of the definite integral? It was in this left-hand part where you're going from a to b, that was delta x equals b minus a divided by n. You take the top number, subtract the bottom number, and divide by n. Whereas if you look at the definition of the Riemann sum definition of this integral on the right, what would delta x be? It would be the top number minus the bottom number divided by n. A minus b divided by n. And so notice that the delta x's on the right and the left, they're negatives of each other. So right there you see that dx, that delta x, controls the sign relative to the order that the a and the b are in. Another property is the sum difference property. The integral from a to b f of x plus or minus g of x dx equals the integral from a to b f of x dx plus the integral from a to b g of x dx. And this you can pretty much see how this would come about by reverting back to Riemann sums, limits of Riemann sums, and just use the sum difference property for the sigma and for the limits, and everything will fall out this way. Also, we have a constant multiple rule. The integral from a to b of c f of x dx equals c times the integral from a to b f of x dx. In other words, that constant c can factor out of the front and come out like this. And again, you can check this by working out the limit on the right, or the integral on the right, as a limit of Riemann sums, and let that c factor out of the sigma and then out of the limit, and the next thing you know, you have c times the limit of the Riemann sums, which would be this integral. Now, before we go on, there's one more thing that I should mention. In all of these integrals, that definite integrals, just like with the indefinite integral, there's a dx at the end. Like the integral from a to a f of x dx. And you may have noticed this already, that where that comes from, it's just a streamlined version of the delta x in the Riemann sum definition of this definite integral, right? The integral from a to b f of x dx was the limit as n goes to infinity f of x sub k star times delta x. The f of x is sort of a streamlined version of the f of x sub k star, and the dx is a streamlined version of the delta x. But all this is to say that that's where it comes from, but don't forget to write that dx. It's part of the notation. Now here's another property, and this one's going to look a little bit strange at first. The integral from a to b f of x dx equals the integral from a to c f of x dx plus the integral from c to b f of x dx. And here c could be any number, but we tend to think about that c as being between a and b. Now, where this is coming from is given by this following picture. Here's the interval from a to b with a c somewhere between a and b. And in this picture, this first little piece of shaded area is the integral from a to c f of x dx. You're integrating from a to c. And then the second darker piece of area, that's between c and b, so that area is the integral from c to b f of x dx. But if you add those two things together, the total area under the curve is the area under the curve in between a and b, which would be the definite integral from a to b f of x dx. So that's the intuitive justification for this fifth property. Now, I've justified it in terms of area. Now, of course, you know that if you would have to be a little more careful with a up minus a down if this function went below the x-axis. This picture is just a sort of a quick and dirty way of convincing yourself that this formula is right. And you can actually prove this formula very carefully using the definition of the definite integral with Riemann sums. But I think it's just better to look at the picture and say, oh yeah, that looks totally reasonable, and just believe this from here on out. Take it on faith. You know, if you ever do take a more advanced calculus class, you might get to the point where you're actually verifying things like this very carefully. But in a first class in calculus, I think it's okay just to have a really good intuitive understanding of why things are true and just move on from there. So more properties of the definite integral. You'll notice the numbering is not sequential. I had 5, and I'm skipping 6 and jumping to 7. I'm keeping the numbering in the book. In the book, the number 6 was the a up minus a down property, although they didn't explain it as well. I think looking at it as a up minus a down is a better way of doing it. But read the book and see what it says. Property 7 says that if f of x is greater than or equal to 0 on this interval, then the definite integral from a to b f of x dx is going to be positive. And it's totally clear why that's true. Just think about the Riemann sum limit in the definition of this definite integral. All of those rectangles would have non-negative height, and the base delta x would be positive. So you're adding up a bunch of non-negative quantities there. And so when you take the limit, you're going to get something that's not negative. It'll be greater than or equal to 0. Also, it seems to make sense intuitively that if f of x is greater than or equal to g of x on the interval from a to b, then the integral from a to b f of x dx is greater than or equal to the integral from a to b g of x dx. And to see why, the rectangles going up to the function f of x, they'd be taller than the rectangles going up to g of x. So it makes sense that the first integral is going to be a bigger number than the second integral. And finally, one more property that we may have occasion to use maybe in the next lecture. And this looks complicated, but it's actually really simple. If f of x is bigger than a number m, but less than a number m on the interval from a to b, in other words, if no matter how you pick x in this interval from a to b, f of x is bigger than this number n, m, bigger than or equal to it, or less than or equal to this number big M, then you get the following inequality. The little m times b minus a is less than or equal to the definite integral from a to b f of x dx, which in turn is less than or equal to the big M times the b minus a. Now this is kind of a technical condition, but sometimes it's going to be useful. It has a really simple picture. Think of it this way. Here's the interval from a to b. So the distance between those two numbers is b minus a. That's the distance between a and b. We've got the graph of our function, y equals f of x. And the integral from a to b f of x dx, that's the area under the curve, the shaded area. So that's what you see right here. And I've drawn this so that the number little m is such that f of x is always greater than or equal to little m. The y value for f of x is always greater than or equal to little m. And also the y value for f of x is less than or equal to the number big M. So here's an x, there's your f of x, but m is way up here. So this condition holds for this function that I've drawn on this interval. Now what I want to point out here is that if you look at this rectangle that has a height of little m, its area is base times height, b minus a times m, or m times b minus a. And that's less than or equal to the shaded area, which is the definite integral from a to b f of x dx. So you see how this is the area of a rectangle, the little rectangle down here? That's less than or equal to this definite integral. On the other hand, think about the expression big M times b minus a. Well, that's height times base of this big rectangle that totally contains that shaded area that's equal to the integral from a to b of f of x dx. And so that would say that height times base, m times b minus a, is greater than or equal to this definite integral. So there you have it. These are some properties of the definite integral. You should read this section. It's kind of technical. The definition is fairly involved, a limit of a Riemann sum. But I want you to take heart in knowing that the way we define the definite integral was important just to give the meaning of the definite integral, these area interpretations. When we go on to the next section on the fundamental theorem of calculus, we'll find really quick and easy ways to compute definite integrals using antiderivatives, to compute definite integrals using indefinite integrals. It's going to be interesting. So read this section, think about these ideas, and I'll see you next time. Have a great day, and goodbye.